This lesson shows you how to develop an error handling strategy for your application. What will your application do when an error occurs? Will it display an error dialog box? Exit the application? Perform hardware shutdown procedures? Send the state machine to a shutdown case? Ignore the error, log the error to a file, or retry the task? To analyze a section of code and determine how it should handle an error, you should ask yourself the following questions. What could go wrong? Can I do anything about it, such as logging the error to a file or reporting the error to the user? What will be the effect of the error on subsequent code? What should be the effect of the error on subsequent code? Because automatic error handling interrupts the running application, you should turn it off for the VIs in your application. Instead, use programmatic error management to control how errors are passed and reported. Here are 5 aspects of error handling: error injection or generation, error propagation, error response, error display, error logging. Error injection is the creation of an error value at the point that something goes wrong in the LabVIEW code. By generating the error shown in this code, I can test how this application handles an undefined or not existing DACMX channel specified by a user. There are many approaches to error propagation. Creating a fork in an error wire to make parallel code paths. Merging errors from parallel code paths. Skipping execution of some nodes when an error occurs. There are many tools to facilitate error propagation: case structures, merge errors function, shift registers. One way to break the error chain is to neglect to wire an error output. This can happen in the case of a 0-iteration for loop. If a for loop iterates 0 times, upstream errors are lost and the output refnum is invalid because for loop output terminals return default values if the loop does not execute. There are 2 options to prevent this issue. Use shift registers instead of tunnels for in-out pairs on for loops to handle the 0-iteration case. If you don't want an error generated during one iteration to be passed to all future iterations, use the merge errors function to merge individual errors after the loop executes. You can test propagation issues using the VI Analyzer Toolkit. The VI Analyzer Toolkit installs with the LabVIEW Professional Development System. If you use the LabVIEW Full or Base Development System, you can install VI Analyzer Toolkit from the NI Package Manager. Run the Error Cluster Wired test in the VI Analyzer Toolkit. This detects sub-VIs and functions with unwired error outputs. You can run the Unused Code test in the VI Analyzer Toolkit, and it will detect unwired output tunnels of structures. You can also run the for loop error handling test. This detects loop-related error propagation issues as we described earlier. It also detects if there are ordering issues in merge errors. How do you know if your error handling strategy is working correctly? To determine this, you should test how your system responds to errors to ensure that your error handling code performs as expected. Create a plan for error testing. Identify errors that are likely to occur in the system. Then, determine how the system should respond to each error. Error display is the act of displaying error information to the end user or code developer. Error logging is the saving of errors generated by LabVIEW to a file for later analysis. If you choose error logging, keep these recommendations in mind. Log all errors, even those that your code handles. Don't forget to log no error events. Add timestamps to the logs to understand when and where the errors are occurring. Develop error handling code for 2 stages, the development and deployed stage. In the development phase, error handling code should be noticeable and clearly indicate where errors occur. This will help you, as a developer, to determine where any bugs might exist in your application. For example, use the Simple Error Handler VI to display the error code and source. In the deployed phase, the error handling system should be unobtrusive to the user. The error handling system should allow a clean exit and provide a very clear prompt to the user. For example, the application could create an execution log instead of displaying intrusive error dialogues. Also, the application should shut down gracefully. For example, setting all outputs to safe states before exiting. The application could also display a dialog box asking the user to contact the developer who supports the application. Then the developer could ask the user to send an execution log, which can aid the developer in troubleshooting the error. One way to inject an error is to do the action that causes the error to occur. For example, you can manually cancel an open file dialog. Try to write to a read-only file. Specify an invalid INI file. Specify an invalid hardware channel. Unplug a network cable. You can interactively configure. Another way to inject an error is to modify your code to cause an error. For example, you could modify your code to send a message for a case that doesn't exist. Or you could inject a specific error code by using an error cluster from Error Code VI or an error ring. You can interactively configure a specific error value on the block diagram at edit time. The following error code ranges are reserved for custom error messages. After injecting an error, you need to verify whether or not your application handled the injected error the way you intended. Verify that the proper errors were reported. Verify that the error handling code handles errors gracefully. For example, critical errors should result in a safe system shutdown. However, non-critical errors should not force your application to shut down. Your application should be able to recover from non-critical errors. Let's say I want to test how this application handles a user specifying an undefined or non-existing DACMX channel. One approach is to inject this error by causing it to happen in the application. In this case, I can just set my AI voltage channel control to an undefined DACMX channel and run the VI. It looks like this application handles this error by displaying an error dialog box and exiting. Another approach is to simulate the error I want to test by injecting the corresponding error cluster in the application's code. To do this, I can go to the location in the code where I want to simulate an error occurring. In this case, I want to simulate the DACMX create channel VI passing out the error -200220. I'll place down an error cluster from Error Code VI and set it to output the corresponding error cluster data for that error code. Now when I run this VI, error -200220 will be passed through the VI. Again, the application handles this error by displaying an error dialog box and exiting. Here's a review of simple error management. For each node, if there is no error, the node executes normally. If there is an error, the node passes the error to the next node and skips executing its normal functionality. The exception is that the shutdown VI functions, such as close file, release queue, and DACMX clear, will attempt to execute regardless of an incoming error. At the end of the VI, typically you will see the Simple Error Handler VI reporting any errors in a dialog box. Local error handling refers to code called in a specific location to immediately respond to specific error codes with an action. Examples of possible actions include preventing the error, ignoring the error, retrying an action to fix the error, correcting something to fix the error, or properly shutting down the code. Another approach is preventing an error by validating inputs. For example, if a control value will be used as the denominator of a divide operation, develop code that checks that the control value is not 0 before proceeding. Or if a control value must be between -10 and 10, then set the control's minimum and maximum values in the Data Entry tab of the Properties dialog box to ensure that the control's value will be in range. Many errors can be ignored. There are many cases when an error may be expected, when the error may be detected in another way, or when the error simply does not have any relevance to the program. An example of an error to ignore is a canceled dialog box. The File dialog ExpressVI returns an error with error code 43 if the user clicks the Cancel button on the launched File dialog. You can use the Clear Errors VI to clear error 43 from the error wire. You can retry actions as a way to try to correct an error. For example, many communication errors can be fixed by waiting for the instrument to finish processing a previous command, or waiting for the network to reconnect and retry the communication. You should generally limit the number of retries or the amount of time that can be spent on retries to avoid infinite loops. When retrying errors, you might also want to display a dialog box to the user to let the user know that your application is retrying a particular action. In this retry action example, if the user enters a non-existing or invalid DACMX channel, the application, to avoid shutting down from the error, can launch a dialog box that notifies the user that their specified DACMX channel is invalid and asks the user to retry entering a valid DACMX channel. Let's take a look at the code that implements this retry behavior. If the DACMX create channel VI outputs error -200220, which is an invalid channel error, you can use the Clear Errors VI to detect the error and remove it from the error wire. If the Clear Error VI detects this error, then its error cleared output will pass a true to the case structure, which then handles the error by displaying a dialog box to the user, asking the user to enter a valid channel. Because you are handling this error by asking the user to retry the action, you can also filter and remove the specific error from this error wire. Let's see this retry action code in context of a full application. If the Clear Error VI does not see the error -200220, then the case structure will execute the DACMX VIs to acquire data and transition the state machine to the analyzed state. However, if the Clear Error VI does see that error, then it will remove the error from the output wire, and the case structure will launch a dialog box asking the user to enter a valid channel and transition the state machine back to the wait for event state instead. Let's run the VI and see this in action. If I use a working AI voltage channel, the application acquires data from the DACMX device normally. If I use an undefined AI voltage channel, the application launches the dialog box, which asks me to try again. You can execute code to directly correct the error. For example, you can provide a default directory or file if the user cancels a file dialog. Or you might close the communication to a device or instrument and reopen the communication. This often clears buffers and fixes some errors. Other errors might be fixed by programmatically adjusting input parameters to the code. When you fix an error by retrying or executing correcting code, you should either filter out the error since it's been handled, or convert it to a warning so that it is logged to the error log. If a section of code must execute whether or not an error has occurred, then ensure that the error will not prevent the code from executing. For example, you typically would always want your shutdown code to execute, even if an error has previously occurred. In this example block diagram, if the incoming error wire contains an error, what will happen in this shutdown code? Will the DACMX write set the analog output channels to a safe shutdown output voltage? In this example block diagram, if the incoming error wire contains an error, what will happen to the shutdown code? Will the DACMX write set the analog output channels to a safe shutdown output voltage? If your application generates an execution log file, the execution log can make it easier for the developer or user to identify issues that occurred in the application. An execution log should include the information necessary for someone to understand the state of the application at the time the data was collected. Typical information include timestamps and state information, such as a state name, configuration values, and state data. In this example, every time the application starts running, it creates an execution log file, which includes the timestamp in the file name. Then, every time the application enters a state, the application logs the current timestamp, the state name, and any configuration values and data acquired or processed in that state. An execution log should log information about critical errors to assist with troubleshooting. An execution log should explicitly log whether the application completed successfully or exited due to an error. In this example execution log, the last entry is that an error occurred, and it gives the error explanation. Because it's the last entry, I can tell that this error caused the application to exit. Due to the error explanation and the previous entry, I can deduce that this error occurred in the acquire state, and that this error occurred because the AI voltage channel was blank, and therefore not specified. In this example execution log, the last entry is success, so I know that the application completed successfully without any errors. Having an explicit entry for success is very useful, because if I see an execution log that doesn't end with a success entry, I know something has gone wrong. This is an example of how you can code the implementation of the execution logs that you just saw. Click each function for more details. Here's a summary of what you've learned in this lesson.